So assuming we have the equation of motion, okay, here is being written in matrix form. So that's the equation of the motion, and each of the x here, that is a vector component, and that is our degree of freedom. And for example, if we consider two degree of freedoms, so here we assume the degree of freedoms still follow harmonic motions, okay, but they are in different amplitude. So we have this assumed harmonic motion introduced into equation motion. So you can see the acceleration term basically, because of the harmonic, basically acceleration is equal to minus omega squared times displacement. Because here we have, say, x1 equal to, say, cosine omega t plus v. Then you can see x1 double dot equal to minus omega and cosine omega t plus v. So that's the reason why here we have these things up here. Okay. So once you have this one, then we begin to solve the typical eigenvalue problems. Okay, why that is the eigenvalue problems? Go to study in details. This form basically is equivalent to the standard of the eigenvalue problems. So that process starts with this. We take the determinant of the coefficient of the x true terms. So here, if you combine the coefficient of the x term, which means this term plus k, okay, that is here. So we solve the determinant of this one equal to 0, and then you can manually solve for the natural frequencies, or you can solve it by MATLAB. And once the natural frequency has been solved, and then for each of the natural frequencies, we can solve for the relations between the amplitudes. Okay, the relation between the amplitude is called the eigenvectors. Okay, for example, for omega 1, the relation is in 1 to R1. For different omega, that have a different ratio. Okay. And this one is called the modal vectors. Modal vectors simply, again, for different natural frequencies, we will have a different modal vectors. And each modal vector simply describes the relation between each component of the amplitude. Okay? So for 2 degree freedoms, we have 2 natural frequencies, 2 modal vectors, and come to the last step, and that is the most important step, is this. The solution simply is the linear combinations of the modal vectors. Okay, this is a very important concept. So here, this is the 2 modal vectors associated with omega 1 and 2. Here I made a typo here, so let me add it up here. So that is what? Okay, so associated with each natural frequencies, we have the modal vectors. And here, in linear combinations of the modal vectors, so this is a modal vector, these are modal vectors. The linear combinations is through such a form, okay? And that still assure the harmonic form, and that is for this one, because it associated with the first modal vector, it must be in harmonic form of the first frequencies in a similar way that the second frequencies. Okay, in this way, the alpha is the amplitude of this harmonic, T1 is the phase angle, and similarly beta and phi that associated with the second mode. Okay. So in total, for example, in 2 degree freedoms, we have 4 unknowns, and we should be able to solve by the initial conditions. So this page basically summarizes what we've been done in the last 3 lecture hours. Okay, and I said this one very quickly, but this will be the big guideline. And to each of the steps, actually, formulating the equation of motion, we take about 1 lecture hours. And here we formulate in the matrix form and talk about the eigenvectors, eigenvalue problems, then that's spent about 1 lecture hours. And then how to solve for this one, basically you can refer to the Friday last week. Okay, so that is basically involving, hopefully this page serves as the roadmap for each of you to dig into the details. Okay. So if we would have more time, I will come back to do more examples, but let me move on to the new sections.